Hey everyone, welcome to another deep dive. This week, we're going to try to tackle the concept of rate of change.
Yeah.
It's something that your seventh grader is going to be encountering in their math this week with the Classical Conversations, the Math Map curriculum. So
Yeah.
we're here to help you feel confident and prepared
Yes.
to be able to guide them through that. And we have a great resource for us to use this week put together by homeschooling experts over at Scholars and Socials.
It's like a quick coffee break for you before you have to actually teach
Yeah.
the material.
All right, so let's start with something familiar. We all know what miles per hour are. If you're on a road trip and you're calculating how many miles you've gone and dividing it by how many hours you've driven, you're figuring out your average speed over that distance.
Yeah.
And that's actually a concept we use all the time, is average rate of change.
And then calculus allows us to zoom in on instantaneous rate of change, so the speed at any moment.
Okay.
Not over a whole trip,
Yeah,
but
right.
at a specific moment.
So that's where the derivative comes in. When driving 55 miles per hour, my actual speed constantly changes, but the average speed is 55 miles an hour. So like you're accelerating, braking, maybe cruising for a little bit.
Mm-hmm.
But the derivative gives us a way to pinpoint the exact speed at any given moment.
Yeah, it's like a snapshot. Connect this to things that we see every day, too. For example, if you think about a ladder sliding down a wall,
Mm-hmm.
the top of it is moving down at a certain rate.
Yeah.
The bottom of it is moving away from the wall at a certain rate. These changing speeds or rates of change are connected. And this idea is what we call related rates. It's how different rates of change can influence each other. Like blowing up a balloon, the radius is changing as the volume changes, and those rates are related.
And I know that our source material gets into a table of derivatives and rules for calculations and all of that, but don't worry. For this deep dive, we're just focused on the concept,
Yes.
not the complex formulas.
Keeping it 7th grade friendly.
The goal is to help you grasp the core idea of rate of change so you can confidently explain it to your seventh grader. We want to empower you, not overwhelm you.
I like it.
Okay, so how do we make this clear for our seventh graders?
Yeah.
Well, our source material has this really great frequently asked questions section that tackles common concerns, and it starts with what is the fundamental concept of the derivative?
Perfect, because I think that's where most people, myself included, might need a little extra clarity.
Absolutely, and it really goes back to that,
Yeah.
capturing that moment.
Of change, the instantaneous rate of change instead of the average speed over a whole trip. This is zeroing in on the speed at that moment as you pass mile marker 123.
Okay,
That would be the instantaneous rate of change.
got it. They mentioned that visually this relates to something called a tangent line. Didn't we learn about those in geometry?
Yes, it's a line that just grazes a curve at one point.
Okay.
And the slope of that tangent line tells us how steep the curve is right at that spot, representing the rate of change
I see.
at that exact moment,
Got it.
like a skateboarder going down a ramp. The steeper the ramp, the faster the rate of change.
Okay, that visual helps a lot, but I still get a little tripped up on the difference between average rate of change and instantaneous rate of change.
Let's go back to those cookies you were baking. If you bake 24 cookies in 30 minutes, your average rate of change is 24 cookies per 30 minutes. But as you're baking, sometimes you're putting cookies in, sometimes you're taking cookies out. The instantaneous rate of change would be like, how many cookies are you putting on the sheet right now?
So the derivative helps us zoom in on those specific moments, slow motion replay.
Yeah.
And the source material really emphasizes this isn't just theoretical. Derivatives help us understand how things are changing constantly in the real world, from the growth of plants to the movement of planets.
Now, I know we said we'd stay away from complicated formulas, but let's just give our homeschool parents a tiny glimpse at a couple of basic rules.
But promise me we're keeping it seventh grade friendly here.
I promise. The first rule is incredibly easy. It's the constant rule. A constant value, its rate of change is always 0. Think of a flat line on a graph that's just staying the same.
Yeah.
Not going up, not going down, its derivative is 0. And then another one you mentioned earlier is the power rule.
Yeah.
If you have a variable raised to a power like x squared,
Right.
the power rule gives us a shortcut to find its derivative.
Okay.
Don't worry about the specifics now.
Right.
Just know that this rule helps us figure out how functions change when variables are raised to powers.
Okay, that's enough formula talk for me. They mentioned something about using the first and second derivative to analyze how a function behaves. This is where things start to feel a little bit abstract.
It might sound complex, but it's actually quite intuitive. The first derivative tells us whether a function is increasing or decreasing.
Okay.
At any given point, imagine a roller coaster. If the track is going up, it's increasing. The first derivative would be positive. If the track is going down, it's decreasing.
Got it.
The first derivative would be negative.
So it's like it gives us the direction
Yes.
up or down.
Exactly. And then the second derivative,
Okay.
this one tells us about the shape of the curve. Is it curving upwards like a smile or downwards like a frown? If the second derivative is positive, the curve is concave up like a bowl. If it's negative, it's concave down like an upside down bowl.
So the first one tells us if it's increasing or decreasing, and the second one tells us how it's curving.
Yes.
Two different lenses
Precisely.
for the same thing.
And by using both, we can get a much deeper understanding of how a function behaves.
This is reminding me of those nature documentaries where they show how a plant grows with like time-lapse photography.
Yeah.
And you see the overall upward movement.
Right.
But then also like those curves and bends as it reaches towards the sun.
Yeah.
Maybe calculus is nature's secret language.
It's a beautiful way to put it.
I like that. They also tackle this question, what does it mean for a function to be differentiable? Is this where we need a PhD in math?
Not at all.
Okay, good.
Simply put, a function is differentiable if its derivative exists at a certain point. Think of it like this. If you can draw a smooth tangent line at that point on the graph, the function is differentiable there. But if there's a sharp corner or a jump in the graph, it might not be differentiable at those points.
So a smooth, continuous curve
Yes.
is key.
Smoothness and continuity are important for a function to be differentiable.
So why do we even care if a function is differentiable?
It's like having a toolbox full of very specialized tools.
Okay.
If a function is differentiable, we can use all of those calculus tools to analyze it and unlock all sorts of information about its behavior. It opens up a whole new level of understanding.
So it's like having the right key to unlock the door.
Yes.
We've unlocked some doors today.
I think we have.
Hopefully our homeschool parents are feeling more confident about tackling rate of change and derivatives
Absolutely.
with their 7th graders.
And remember, you don't have to be calculus experts to teach this.
Yeah.
Focus on the main concepts. Find those everyday examples and encourage that curiosity.
Yes, and don't be afraid to dive in and ask questions and even have fun with it. One thing that really struck me in the Scholars and Socials document was how they connect rate of change to personal growth. They asked this really thought-provoking question, does God use a heavenly calculus to see my changes with mathematical precision?
It's such a cool connection.
Yeah.
They point out that life is not a smooth, linear process. Spiritually, physically, academically, in every area I am growing, changing, developing. Some days show more growth, while on other days changes are imperceptible.
So true. Sometimes we feel like we're making huge strides,
Yeah.
and other times we're just like barely moving forward.
Yeah.
Like those graphs we were talking about, sometimes the function is increasing rapidly and other times it's plateauing.
But even on those plateaus, there's still change happening, maybe in ways that we can't see. Just like a derivative can reveal subtle changes in a function. Maybe there's a bigger perspective that can see the nuances of our growth even when we feel stuck.
That is really encouraging.
Yeah.
It reminds me that progress isn't always linear. There are going to be ups and downs, curves and bends along the way.
It's all part of the journey.
This deep dive has been so helpful, not just for understanding the math, but like for putting it into a bigger context.
I agree. We've covered a lot of ground today, from the basics of rate of change to the complexities of derivatives, and even touched on that philosophical side of things. Hopefully you're leaving with a renewed sense of confidence and a deeper appreciation for how this fundamental concept plays out in our lives.
Absolutely. And homeschool parents, remember, you don't have to be calculus experts to guide your 7th graders through this. Just focus on those main ideas, find those everyday examples, and encourage that curiosity.
And who knows, maybe those late night math sessions will spark some really cool conversations about the nature of change growth and the wonders of the universe.
Well, thank you so much for joining us on this deep dive into rate of change. We'll see you next time for another fascinating exploration.